Alright, so let's start today's discussion by considering a notion from elementary ring theory that we already know, namely the direct product of finitely many rings. Say these are finitely many rings, A1, A2 up to AN. Then their direct product is the ring of all sequences, finite sequences of elements xi from these rings AI, where the ith component xi comes from the ith ring AI, and where addition and multiplication are defined component wise. So to put things more simply, this is just as a set, it's the Cartesian product of these AIs. And that's it. Addition and multiplication are defined component wise. You already know from ring theory that this is a ring. Now additionally, note also that because our rings are commutative, this is also a commutative ring, and our rings also, each one of them has an identity element 1, and as such A also has this identity element. So according to our definition, this A really is a ring that we can call ring here in this study. Now wherever you have the direct product of some rings, naturally these projection maps arise. So each such projection map Pi corresponds to one index I. What Pi does is this: Pi maps the direct product onto the ith ring AI by mapping this input to its ith component xi. And these are called projections because in a sense it's like shining light on this ring and looking at the shadow of this ring that is cast on this component only. That is why they are called projections. And you further know that each such Pi is a ring homomorphism, and not just that, it's an onto ring homomorphism. Now next what we are going to do, we will take a single ring and some finitely many ideals. Each ideal will give rise to a quotient ring of that ring, and then we will take the direct product of those quotient rings and then investigate the relationship between that direct product and the original ring. So let's see what that gives us. So let A be a ring and this I1, I2 up to In be ideals of A. So we are now looking at a single ring and n number of ideals in that ring. So then we can consider all the quotient rings of A by these ideals. That way we will get n rings and we can consider their direct product. And we are defining a function phi from the original ring into this direct product by this rule. What it does is that it takes an element x from A and maps that onto this n tuple. Does it make sense? Let us see. What is the first component of this n tuple? X plus I1. So it's the coset of the ideal I1 by the element x of the ring A. So obviously this coset is an element of the quotient ring A slash I1. Okay. Similarly, x plus I2 will be an element of A slash I2 and so on. So this really is an element in this direct product. And it's absolutely straightforward to show that actually this is a homomorphism. There is no twist in this proof of the fact that this is a ring homomorphism. I should have written it here because it's there in the book. I forgot to write. Define this, then phi is a homomorphism. Okay. So we do not really have to, if you want, you can verify this, you should verify this, but this is so straightforward that after some stage, you just accept some things. You will know yourself when you see something that it is so natural that it should be true. Unless something goes wrong later with it, then there is some kind of problem with your understanding. But if you just think of it mentally, there itself it will become clear that this is a homomorphism, and that too in a very natural way. Okay, so leaving that fact aside, let us now come to this proposition which says something about this function phi. The first part, it has three parts. The first part, however, says something about the ideals themselves. So what it says is that these ideals are mutually coprime. That means any two distinct ideals I and ij, their distinctness is ensured by having I and j different. So any such two distinct indices give us coprime ideals II and ij. If that is the case, then the product of these ideals, we already know what we mean by product of finitely many ideals, that is equal to the intersection of all these ideals. Does it not remind you of something similar that we have already done in the case where we have two ideals? Yes. You remember, towards the end of the previous video, we proved that if two ideals are coprime, then their product equals their intersection. So it's the general version of that. And in fact, that result will be used in its proof. Next, in part 2, our function phi will be surjective, that is onto if and only if this condition is true. That is, the ideals, these i's are mutually coprime. Any two distinct ideals from that list are coprime. And number 3, phi is injective, that is one-to-one, if and only if the intersection of all these ideals is the zero ideal. This is the easiest of all these three, because a moment of reflection will show that this intersection is nothing but the kernel of this homomorphism. But anyway, let us next see the proof of this. So this is the proof. In the proof, of course, first we are going to prove 1. And because we already have the result for two ideals, so it's natural to apply induction on the number of ideals, and that's what we do. We apply induction on n. And the case n equal to 2 has already been proved in the previous video itself. So assume that n is greater than 2, which means that we already have all these ideals I1, I2 up to In, and now n is greater than 2. That means n is at least 3. It may be more than 3 also. And we are assuming that the claim is true for these ideals, these first n minus 1 ideals. Note one more thing, that the hypothesis that we have imposed on these ideals is there for our n ideals, namely that any two distinct ideals from our list of ideals are coprime. That is true, that is there. In that situation, we are assuming that the claim is true for this first n minus 1 ideals. So the hypothesis is applicable to these ideals as well. In particular, if we leave the last ideal out of the list, these also are mutually, that is pairwise, coprime. So obviously, by this assumption, which is our induction hypothesis, the product of these ideals will be equal to their intersection. Okay, so we have this with us, and we are giving it a name also. Let us call it J. Okay, so we let it sit like this here, and next we concentrate on the fact that each I, where I varies from 1 to n minus 1, is coprime with the last ideal In, that their sum is the entire ring 1. And we know, we have already seen in the previous video, that when that happens, we can find one element here and one element here, so that their sum is the identity element of the ring. and this is happening for each such I. So that way we get some elements xi in ii. Here I changes. Here however, here also I changes, but the ideal does not change. All these yi's belong to in, whereas each xi belongs to ii, that particular ii. Now next what we do, we take the product of all these xi's. Do not forget that I is varying from 1 to n minus 1, not n. Okay. So accordingly we get this product. So then in place of xi we can write 1 minus yi. The product remains the same. However, this is congruent to 1 modulo this ideal in. What does it mean? Actually it means that if we take the difference of this element, this is after all an element, and 1, that difference belongs to the ideal in. This congruence modulo in is just a fancy way of writing that thing. Is it true, however? Let's think of it, okay. If you carry out this multiplication, this is the product of terms like 1 minus yi. So 1 minus y1 times 1 minus y2 all the way up to 1 minus yn minus 1, because that's the last one in this product. Now if you do the multiplication fully, what will you get? One of the terms in that entire sum after doing the multiplication is 1, because 1 times 1 times 1, so a 1 is always there. Besides that, we have a product of some yi's. Many different kinds of products will be there. However, all those products belong to in. Why? Because in all of them, we are actually multiplying some finitely many elements of the ideal in, and because it's an ideal, so the product stays within the ideal, and the sum of all those products belong to yn as well. That means this product we are looking at is 1 minus or plus, it does not really matter, an element of in. And from that, if you subtract 1, then you are left with an element of in, and that's why this belongs to in. This minus 1 belongs to in, or in other words, this is congruent to 1 modulo in. So next, what do we have after this? Let's see. As a result of this thing, we next have in plus j equal to the whole ring. So this j and the last ideal in are co-prime. However, it may not immediately be clear how we have that from this. To see, let me just write a few more things. See this product, the product of the first n minus 1 xi's. Let me give this product a name, say let me call it z. Then what are we getting from this? That z minus I. Let me just do the rough work here. Z minus, not minus I, minus 1 is in in, right? So if I call z minus 1 something, say y, then what am I getting? Y plus z, or minus y plus z is equal to 1. Minus y plus z is equal to 1. Now, where is y? Y belongs to in, so minus y is also in in. This is coming from in. Where is z coming from? Note that all these xi's belong to the ideals ii, they are corresponding ideals. So by the definition of the product of these first n minus 1 ideals, the product of this xi's belongs to this product. It is actually a generator of this ideal. It is one of the generators. Do you remember that by definition in this ideal, every element is a finite sum of products of elements from these ideals. So these products generate this ideal. This is one such generator. So this is coming from this or J. So we have an element in In and we have an element in J, and their sum is the identity element of the ring. So by what we discussed about two ideals being co-prime in the previous video, In and J have to be co-prime. So that way we have this. Alright. But if they are co-prime, then I can apply the claim in the case n equal to 2 to J and In. So the product of J and In will be equal to their intersection. However, if you look closely, this product is nothing but the entire product of all the ideals II, starting with 1 and ending at n. So if you consider the first n minus 1 ideals in this product, you are getting J, and with that one last ideal In. So that's why it is J times In, which by this argument is J intersection In. And here we are using the case n equal to 2 that we already have with us, which is in fact our induction basis. And what is this intersection? You already know that J, besides being this product, is also equal to that intersection. So you intersect In with the intersection of all the first n minus 1 I's. So you get the intersection of all the I's. So that way you have the claim in the case where we have n ideals, based on the assumption that our claim is true for n minus 1 ideals. So this completes the induction, and that is part 1. Next let us see part 2. Part 2 is an if and only if statement, so we have to prove it both ways. Let us first assume that phi is surjective, that means phi is onto. So if phi is onto, any element of the direct product of those quotient rings will appear as a phi image of some element of A, of the ring A, original ring A. In particular, you can consider this entuple of cosets, where the first coset is 1 plus I1. The other cosets are, however, the i's, the respective i's. This should also be equal to the phi image of some element x from A, but by the definition of phi, this is x plus I1, x plus I2 and so on up to x plus In. So this entuple is equal to this entuple. That means x plus I1 is equal to 1 plus I1 in particular. And but there is a result in group theory which tells us that two cosets are equal if and only if the difference of their representatives is there in the subgroup, or in this case ideal. So that means x plus I1 equal to 1 plus I1 means x minus 1 belongs to I1, or in this congruence language, x is congruent to 1 mod I1. At present, this congruence things may seem extremely unnecessary and unnatural also. However, the more we use them, the more natural they will become. Okay, but anyway, similarly, x plus I2 is equal to I2 means x is an element in I2, and in this language, x is congruent to 0 modulo I2. And in fact, I have written that below that also. So x minus 1 in I1 means 1 minus x is also in I1, because I1 is a group after all under addition, and x is in I2. So their sum will be in I1 plus I2, but that sum is 1. So this proves that the ideals I1 and I2 are mutually co-prime. They are relatively prime. And one can similarly show that I1 is also relatively prime to the other IIs. You have considered this congruence here. Similarly, you also have x congruent to 0 mod I3 say. So in place of I2, you can do all these things with I3 and I1. So that will give you I1 plus I3 equal to the whole ring. So that way, I1 is co-prime with all the other ideals. And in a similar manner, every II is co-prime with every other Ij. For example, say in place of this I1 you want to take I2, then you have to change this element. In place of this element you would take I1, 1 plus I2, I3, I4 up to In. So that will give you all these things about I2. So that way surjectivity or ontoness of phi implies that the ideals are mutually co-prime. Now we have to prove the converse, that if they are mutually co-prime, then phi has to be surjective. So let's see that now. Conversely, we assume that each II is co-prime with each Ij if I is not equal to j. And now our aim is to prove that the function phi is surjective, it's onto. Now in particular, from these relations, we get the fact that I1 is co-prime with the other IIs. Okay, so let's concentrate on this fact. And so we are going to get these elements same as before. Ui plus Vi is equal to 1 for all these i's starting from 2 and ending at n, such that all the ui's belong to I1, but these individual vi's belong to the corresponding ideals II. Now what we do, we consider this element x, which is the product of all these vi's, not the ui's, okay. The product of all these vi's, where of course I starts from 2 and ends at n. Then, just like that previous calculation, in place of each vi you write 1 minus ui and then you carry out the multiplication. In that product, which now is like a sum, you have a 1 and the rest of the sum is an element in I1. So from that, if you remove 1, you are left with an element in I1. In other words, this product minus 1 belongs to I1. So this is congruent to 1 mod I1. Or in other words, x is congruent to 1 mod I1. And what about the other IIs? Well, for the other IIs, it's really easy to see that, because say you, for the sake of specificity, I take I equal to 2. Now V2, that specific element belongs to the ideal I2. Now if I multiply with V2 any ring element, in particular the remaining VI's, then that product will also be in I2, because I2 is an ideal. So that way x is in I2, and that way x is in every II where I is greater than 1, or in other words, x is congruent to 0 mod II. Now if I calculate the phi image of x, by definition of phi, it will be x plus I1, x plus I2, and so on up to x plus In. X plus I1 is equal to 1 plus I1 because x is congruent to 1 mod I1. Similarly, x is congruent to 0 mod the remaining ideals. So x plus each such II is equal to that II. So that way I get this element. However, now what do I do with this? Let's see. So after getting this fact, what we next do is we choose any element z in A. And then you may notice that just like your ordinary congruence from number theory, which involves numbers, Here also congruences can be multiplied on both sides by ring elements. You can multiply this congruence on both sides by z, obtaining the congruence that zx is congruent to z modulo I1. Is it really true? What is the meaning of this congruence? It means that x minus 1 belongs to I1. Now, if you multiply x minus 1 by the ring element z, that is also in I1 because I1 is an ideal. However, z times x minus 1 is zx minus z. That is in I1, which you express in this language, it looks like this. So, yes, it is true in fact. And the fact that these congruences give you these congruences, that's easier to understand. This means x belongs to I1, so zx also belongs to I1, or in other words, zx is congruent to 0 mod I1. Now, with this information, if we calculate similarly, just like that one, phi of zx, we are going to get z plus I1, I2 and so on up to In. Okay, but are we really going to show that phi is surjective with this, or are we moving in circles? What should we do after this? This by itself doesn't show that phi is surjective. It, however, has shown something else. You see that we seem to have shown that every element in the codomain ring, or in that second ring, which is the direct product, which is of this form, has an inverse image under phi. This element is not as general as we would like to have an element in that product ring, because all its coordinates almost are the zero ideals. The zero elements in those quotient rings, except the first component, which is just any coset. So, we have got generality at least here. Okay, this is any element from the quotient ring A slash I1, and we want to have any elements in these places as well. But whatever we did with the first component, can we not do similar things with the second component, third component? Yes, we can. And that is why we have this next thing. To express a little more clearly what I said just now, we rewrite this like this. That is, for any z1 belonging to A, in place of z we are writing z1. There exists k1 belonging to A, which actually is just this zx, such that phi of k1 is z1 plus I1, and the remaining components are just the i's. In general, so this is whatever we did here is for the first component, for the case I equal to 1. In general, for any I and any zi in A, there will similarly exist a ki in A, such that the phi image of ki is an n-tuple of cosets of these ideals, where almost all the i's are just i's, except the ith component, which is that zi plus ii. So, you are actually looking at n such equations, phi images. Now, if you add them up, because phi is a homomorphism, this will be equal to phi of k1 plus phi of k2 and so on up to phi of kn. And then you write these things in place of those phi images and then add them up. That gives you this general element of the codomain ring. So, that way any element in the codomain ring is the phi image of something in the domain. That is why phi is surjective. So, that is part 2. Next, let us go to part 3. So, in part 3 we have to prove that our homomorphism phi is injective, that is 1 to 1, if and only if the intersection of all these ideals is equal to the 0 ideal. So, it will be enough to show that this is the kernel of phi. That is not difficult to see. This is what our phi is, right? Phi is the function from A into this, and this is the rule for phi. So what do you think should happen to the element x from A if x belongs to the kernel? Phi of x will be the zero element of this ring. It's a product ring, right? And what is the zero element in this ring? That is that n tuple where each component is 0. The zero element in that corresponding ring. Now each ring here is a quotient ring or a factor ring. So in this ring, for example, the zero element is the ideal II itself. That means we should have I1 here, I2 here, In here. In other words, x plus I1 should be equal to I1, x plus I2 should be equal to I2. So that tells us that x has to belong to each II. So x has to belong to the intersection. So that way we see that any element in the kernel is in the intersection. Conversely, if you take any element from the intersection, then that element belongs to each II. So the coset that that element will give us of that II will be II itself. So the phi image of that element will be the zero element in this ring. So this is also contained in the kernel. So this itself is the kernel. And we know that a homomorphism is one-to-one if and only if the kernel is the zero ideal. I am talking about ring homomorphism. So that is why that's a necessary and sufficient condition for phi to be one-to-one, that this becomes 0, and that ends the proof. And let's end the video here itself, and tomorrow I think we have calculus. Yeah, so see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.